Hello everyone, we are going to be looking at an introduction to thermochemistry today. You should have your fill in the blank notes to follow along with the slides here. So make sure you're filling everything in as we go. There will also be some check-in questions, so when you get to those, listen to the question, read the answers, pause the video, try it to see if you can answer it, and then play it to get your answer. So the current unit we are on is about thermochemistry. Thermochemistry is defined as the study of energy transfer in the form of heat during chemical reactions and physical changes. So we've looked, so far in this unit, we've studied a particular chemical reaction called combustion. And in our last unit, we did our heat stations where we looked at some physical changes like ice melting and heating things with the lamp, like the sand and water heat station, that kind of thing. So those are physical changes when we're just warming something up or cooling something down, changing its state of matter. If we're going through a chemical reaction, then we're changing the chemicals, and that's where our combustion comes in. So thermochemistry is all about that heat transfer when all of these things occur. When we study thermochemistry, we're dealing with temperature changes, and those temperature changes are caused by the heat being exchanged between things, that heat energy. So temperature and heat are not the same, and we're going to explore that difference in these notes. So what is energy? Well, we have three types of energy that we look at in chemistry. We look at thermal energy, or heat, and that is energy that is transferred from one object to another due to particle collisions or light. So when we studied conduction, convection, radiation, that thermal energy is what we were transferring. We were transferring heat energy between things. We look at kinetic energy as well. Kinetic energy is energy due to the motion, it should say of particles, sorry about that, not or particles, of particles, and we measure that by our temperature. So when things are at different temperatures, they have different amounts of kinetic energy, and when they are at different temperatures, they can exchange that energy, which we call heat, from one to another through particle collision, light, or convection currents. So differences in temperature mean they have different amounts of heat contained in them, and they can transfer that thermal energy. The third one is called chemical potential energy. So chemical potential energy is energy that's stored within our chemicals. When we break and form new chemical bonds between things, we can exchange that energy with its environment. So when we do a combustion reaction and we burn those hydrocarbons in that oxygen, we're breaking up bonds, we're forming new ones, and we can give off energy. We also have reactions that can take in energy and store extra. So those are three types of energy that we can look at. So let's check in on our learning here. What type of energy do we get from a combustion reaction? Again, thermal energy, kinetic energy, or chemical energy, or all of the above. So take a moment, pause the video, think about your answer. All right, hopefully you've picked one. So it is actually all of the above. So we deal with all three. Thermal energy in the fact that the combustion reaction is giving off that heat and light that we can feel, that thermal energy. The kinetic energy is those particles moving faster due to the temperature changes. And chemical energy is where the breaking and forming of those chemical bonds to fuel that fire. So it's all of the above are accounted for and found in a combustion reaction. All right, so something that governs all of thermochemistry and this idea of heat transfer is called the law of conservation of energy. And this law states that energy cannot be created or destroyed. It can only change forms. So for instance, in our combustion reaction, it's changing from chemical potential energy that's stored in our chemicals to thermal energy through that heat that we're giving off, which is changing the kinetic energy of the particles and speeding them up, right? So we can transfer it between forms, but we can't create it out of nothing, and we can't destroy it and get rid of it. We can just change it. If one thing loses energy, something else has to gain it. So if some energy is going into something, it has to, we get energy in and energy out. It has to balance each other. All right, there has to be an equal thing there. So let's check again. If heat is lost from a system or a substance, it dissolves into the atmosphere. Is that true or false? Take a moment, think about it. All right, it should be false. If something lost heat from a system or substance, it has to go maybe into its environment. It has to go somewhere. It doesn't just go away or dissolve. Okay, now we're going to explore a little bit more on temperature versus heat itself. So how do we have this difference between them and what's involved in each? So temperature, remember, is that measure of particle movement, that average kinetic energy, how fast those particles are moving. And it's an average. Not every particle is moving the same speed. Some are moving faster, some are moving slower, but that average is what our temperature shows us. So when we look at temperature, it is only dealing with the movement of the particles. Okay, only dealing with movement of the particles. Heat, however, is a little more involved. Heat is the energy that can be transferred due to the particles moving. So it is a transfer of that energy between things. Now, this is going to deal with how fast they're moving, the amount of substance we have, and the type of substance. So all of those things are going to factor in to how much heat we can actually transfer. The only thing that tells us how much temperature we have is the movement of the particles. When we're looking at how much heat we've transferred, it's going to deal with how fast they're moving, their temperature, the amount or mass of the particles, because if you have more stuff, you're going to have more heat, and the type of substance. Different substances are going to transfer heat differently, just like we saw in some of our heat stations. And we'll talk more about that as we go through this unit. So let's take a look at this question. We've got two containers. Container A, let's say that the liquid inside both is water. They're equal size containers. They have different amounts of water, but they're at the same temperature. So which one do you think contains more heat energy, more total energy? So take a moment and think about it. All right, so it would be letter B. Okay, why is that? You have a place to record this part on your paper. So letter B, even though they're at the same temperature, they have the same motion of their particles. Letter B has more of the substance, more mass, so therefore it can contain more energy. So if we imagine that this volume had a certain amount of energy, let's call that amount of energy X, this one has that plus maybe about another 2.5 of that. So it's got that same amount of energy, and maybe half of that energy, right? So it's got like 2.5 times that amount of energy. So it contains more total heat energy than the one with less water. So even though they're the same substance and same temperature, the more mass you have, the more heat energy would be contained in it. All right, now let's take a look at heat flow. We've talked about heat flow in terms of conduction, convection, radiation, but which way does it always go? Heat will always flow from a substance at a higher temperature to one at a lower temperature. On your paper, it ends there. I want you to add this rest of this. So it will do that until the temperatures are equal to each other. This is called thermal equilibrium. Okay, so they will exchange energy from hot to cold until their temperatures are equal. Right, until they are equal. So we'll talk about an example of that. So this thermal equilibrium. So let's try a question around this one. Let's think about it. It says, which one of the following examples is correct? And actually we have two questions on this one. So take a look and decide your answer. Heat will flow from a counter to hot coffee. Heat will flow from a spoon to hot soup. Heat will flow from ice cream to your hand. Heat will flow from your hand to the tabletop. And think about our tabletops in class. How do they feel? All right, so we should have, it will go from our hand to the tabletop. So the other ones we're trying, so A says from the counter to your hot coffee. The hot coffee is hotter, so it should go from coffee to counter. Similar with B, it should go from the soup to the spoon because the soup is hotter. Similar in C, your hand is hotter than the ice cream, so it should go from your hand to the ice cream. If we think about our science tabletops, right, those tend to feel cold. So they feel cold because your hand is giving away the energy to the tabletop. So you're losing energy that's going into the table. So that's the direction of heat flow from you to the table. So that energy will transfer again until they are the same temperature. So let's take a look at this one. This one's a little bit more difficult. Well, a little bit more thinking. So we're going to, again, pause it, think about it, and then check your answer. So you have two pieces of metal that are both 10 grams, so equal masses, same metals. One is at 100 degrees Celsius and the other one is at 50 degrees Celsius. What will happen when they come in contact? So pause it, read your answers, and decide what you think. Okay, so hopefully you've chosen your answer. It should be letter C. Heat will flow from the warmer one to the colder one, so from your 100-degree metal to your 50-degree metal, and they will end at 75. Since they're equal masses and the same substances, they're going to transfer heat the same, so therefore they should meet in the middle. Okay, if they were different masses, we'd have to do some calculating to figure out where they would meet and end, but if they're the same substance and the same mass, they would always meet in the middle. All right, because if we look at A, it says the warmer one to the colder one, and they would end at 50. That would be the colder temperature. But if we're transferring heat from one to another, one should get colder and the other one should get warmer, right? So we can't stop where we started, basically. And then the last one, letter D, B is similar. It's saying that we end at the highest temperature, which would, again, that higher temperature one is losing energy. And D is saying we're ending at a temperature higher than they both started at. So that would not work either. We can't heat both up unless they get more energy from an outside source. Okay, continuing on. So we have two terms that we use to describe heat flow. The first one is endothermic. Endothermic is when a reaction or a physical system absorbs heat. So heat is going into your system or substance, okay? Heat is going in, endothermic, okay? Endothermic, going in. Now, how would that feel to us, okay? What do you feel? When a reaction or a substance absorbs heat from you, it's going to feel cold, right? So the heat is going away from you into the container or into the chemical reaction or into the substance, and you are going to feel cold when you lose heat, okay? So something that is endothermic is going to feel cold. Now, we also have a word that describes the opposite of this. Exothermic. Exothermic is when heat is going out of our substance or our system. So that's when a reaction or a situation releases heat. It goes out. That's why it's exothermic. It's exiting the system. So how does it feel? If you were getting heat from a substance or from a system, the reaction releases it towards you. And so you feel hot because you are receiving that energy, okay? So something feeling hot or cold is going to depend on what temperature you and the substance are at and what's going on. If it's a chemical reaction that gives off the heat, then we're going to feel hot. If it's a chemical reaction that takes in energy, then it's going to feel cold. So hot or cold depends on your perspective. Are you looking at you feeling something, or are you just looking at the situation between two objects, okay? Which way is it going? So we really don't describe things. There's not a specific temperature where we have something is hot or something is cold. It really depends on things being warmer or cooler than other objects. Okay. So a way to help us describe heat flow is to better define the situation. So we use terms, the system and the surroundings, to help us, and we define these parts to help us figure out which direction heat is flowing. So what we call the system is the thing we're focusing on. It might be an object, it might be a chemical, it might be, well, basically an object or a chemical. Those are really all it is. So our system is what? That piece of the situation that we are focused on. The surroundings are everything outside of that system. So let's say that we're looking at trying to figure out which way heat is flowing with a cup of coffee. Okay, so we've got our hot coffee, it's in a mug sitting on the table. Well, your coffee is the part you're trying to figure out what's going on with, so that would be your system. The surroundings might be the coffee mug, the table, the air around it. It could be your hand touching the cup of coffee. All of those things would be in the surroundings. So it's kind of immediately outside your system. So the thing you're focusing on is what we would define as the system, and then everything around it is our surroundings. And we defined those things to help us figure out which way heat is flowing, because it can depend on that perspective. So we create what's called a heat flow diagram to help us with this and help us define if something is endo or exothermic. So what we're going to include in our diagram is what objects or substances are in the system, what objects or substances are in the surroundings, and then we're going to use arrows to show the direction of heat flow. And it says a letter Q over here. The letter Q is the variable that we're going to see in this unit. We're going to have an equation in our next set of notes. But Q represents heat. I know that feels weird and you want it to be H, but H is already used for other things. So we use Q. Q is our letter for heat, all right, our variable. Just like, what's another variable we've used? Like D is for density, right? Q is for heat. Okay. The other thing we do is we determine if something's endothermic or exothermic, and endothermic things are going to be positive. We're going to put plus Q because energy is being added to the system. Exothermic is going to be negative, so it'll be negative Q because energy is leaving the system. We're subtracting it from the system. Okay, so we're going to try a couple of these. It's under the flippy part on your notes. Okay, so our first example here is melting ice in a glass of water. So you can see we have a circle with that is labeled system, and then next to it is the surroundings. So we're going to put the part we're focusing on in the system, and then what's around it in its surroundings, and then we'll define the direction of heat flow. So in this, it's talking about melting ice. We've got this glass of water, so our ice is probably our focus, so that's going to be our system. Our surroundings are what's around the ice. Well, we've got water and the glass are both next to or around that ice. So that's our surroundings. Well, which way would our heat go? Which one, and to figure that out, we think, which one's warmer? Well, the ice is cold, the water's probably warm. It's going to go from the water and the glass into the ice. So that's our direction of heat flow. That makes this situation a where we are adding heat to our system, adding heat to our ice. So it is a positive Q. So that arrow is the energy, and the amount would be whatever Q is calculated as. And it's a positive value because it's going into the ice. We're adding it to the ice. So if energy is going into our system, is this endothermic or exothermic? Hopefully you said endothermic, because again, we are adding energy to the system. So we focus everything on what's happening to the system. The system is gaining energy, so it's positive Q, so therefore it's endothermic. All right, let's look at a second example. So we're going to take a look at our candle in a jar example. So in this situation, what's our focus here? Well, we're burning that candle, so the candle is our focus. So the wax, the wick, all of that. So what's happening? Well, around that candle, we had the jar. It was sitting on the table. You could even put your hand, right? Because we had our hand there. We were maybe touch the jar as it was burning, that kind of thing. So where's the energy going? Well, if we think about it, our hand is a good measure of what's happening here. If we are part of the surroundings, we're always part of the surroundings, then we could feel the heat coming from the candle. So it was going from the candle to us, to the jar, to the table. It was warming its surroundings. So that means our Q is going to be negative because the energy is going out of our system. It is being released into the jar, the table, the air around it. That would be another thing we could add to the surroundings. So that makes it endothermic or exothermic. Hopefully you said exothermic because the energy is exiting or going out of our system. Okay. So we can do a heat flow diagram just like these for any situation, and that will help us determine what's going on, which is an endothermic or exothermic situation, and would we get a positive or negative amount of energy. If it's exothermic, we're losing energy, so it's going to be negative. If it's endothermic, we're gaining energy, it's going to be positive. So on the next page, you've got a short assignment on drawing some heat flow diagrams for some of our heat stations that we did. So we're going to work on that and go from there. Thanks, guys.